Hi everyone, this is Yuanlu from Institute of Software, Chinese Academy of Sciences. I'm so glad to present the speeding demo. This is a joint work with my colleagues Bingyong Jing, Zhen Feng, and our co-authors Zhenlian and Chang from University of Sydney. The central problem of blockchain is consensus. The problem definition actually is simple and clean, that is Byzantine fault-tolerant atomic broadcast, in which a set of nodes try to maintain a public ledger of transactions despite some possible corruptions. We require two critical security properties. One is consistency or called safety, that all nodes can output the same ledger. And the other property is liveness. That means all submitted transactions should eventually output. It's also necessary to consider the network condition while designing consensus protocols. We have various network timing assumptions for the purpose. And the first is synchrony, which means there is a known upper bound of network delay. And the second is partial synchrony. That means network delay is bounded but unknown by the protocol designer. And the last is asynchrony, which only assumes messages sent between honest nodes can eventually deliver. And noticeably, if considering asynchronous network, there is a class of asynchronous BFT protocols such as HoneyBadger and Dumbo can be designed to always preserve safety and liveness despite the network environment is how bad. Besides the super robustness, asynchronous BFT consensus is also responsive, as their progress can closely track the actual network speed, so not to depend on the upper bound of network delay. Also, asynchronous protocol is friendly for implementation, as it only has to count taps and the numbers of received messages to make a progress. Although asynchronous BFT protocols have mentioned multifold benefits, they are really rare to use in practice due to inherent efficiency issues. Back to 1980s, seminal FLP impossible result states that no deterministic protocols can realize asynchronous consensus. So such protocols must be randomized, which can be really slow to terminate in practice because of necessary random execution. And such most historic asynchronous BFT protocols are actually pure theoretic, until Miller et al. Presented HoneyBadger BFT and gave us hope such protocols may have practical throughput. And since then, more and more interest are gathered on this promising topic. HoneyBadger BFT is roughly a sequence of asynchronous common subsets, or just called ACS for short. And ACS is a special kind of Byzantine agreement protocol to agree on a set of n-f values proposed by distinct parties. And here f is just a notation for the number of corruption. In HoneyBadger BFT, ACS can be viewed from n reliable broadcast and n asynchronous binary agreements. Here, reliable broadcast RBC emulates a broadcast channel such that each party can use it to disseminate their input transactions. And asynchronous binary agreement, ABA, allows the parties to agree on a single bit. If ABA returns 1, the corresponding RBC is sort of can be eventually complete. If it returns 0, that means the corresponding RBC can be omit. Finally, we can expect the n-f ABAs would output 1. That means their corresponding RBCs would be packed into the final ACS output. HoneyBadger BFT adapted techniques from verifiable information dispersal to have more efficient RBC. So it greatly reduced the communication complexity and realized rather high throughput. But its usage of concurrent ABA protocols is suboptimal, because each ABA is actually a randomized module with a running time following geometry distribution, and expected the slowest ABAs out of the n ABAs would take slow log n rounds to terminate. This actually greatly hurts confirmation latency in practice. A recent study Dumbo BFT resolved that the login latency issue in HoneyBadger BFT can be solved and reduced to expected constant. Its first ingredient is to add a quorum proof to reliable broadcast. The proof can state at least one honest party actually received the broadcast transaction, so all parties will eventually receive the same transactions as long as they're trying to wait it. So we can, we can easily obtain such provable RBC by adding threshold signatures to any RBC protocols we have. Second ingredient of Dumbo is a special kind of asynchronous Byzantine agreement called multi-value validated Byzantine agreement, or just called MVBA for short. MVBA has a predefined external validity condition described by a global predict function, and MVBA's output must satisfy this given predict function. Then we can design Dumbo to assemble a provable RBC and MVBA together by just lighting the MVBA's predicate function to check n-f different provable RBC's proofs. Then, since our MVBA can be constructed by only 2 to 3 ABAs, the latency now becomes expected constant. And this can also give an order of magnitude improvement over HoneyBadger BFT in a concrete performance. But Dumbo still is not fast enough, especially it's much slower than partial synchronized protocols such as HostDelf and BBFT. According to the breakdown of its reading time, the RBC phase actually takes a significant factor in the latency as it exchanges a huge number of cubic messages, and the MVBA phase still dominates the latency because it uses dozens of rounds to terminate. Clearly, to make an even faster asynchronous BFT protocol, it needs us to make the two components faster respectively. We first introduce a cheaper broadcast to have more efficient transaction broadcast phase. We choose provable broadcast as the instantiation, which only has 2 round patterns. In the first round, the sender multicasts input to all parties, and in the second round, only the parties return signatures about the input to the sender, such as the sender can solicit n-f such signatures to form a lock proof to attest the completeness of its broadcast. So we can plug provable broadcast directly into Dumbo BFT, but notice provable broadcast is not as strong as provable RBC because its proof only ensures f+1 honest node can receive the broadcast value. So there needs an extra recovery step after MVBA output to help all nodes to get their missing broadcast outputs. Well, if a node trivially retrieve its missing broadcast output from other nodes, we may have n times communication blow up, which is very unpleasant in practice. So to bound the communication, a node does not directly return a broadcast output, but use Redis-Solomon code to encode the broadcast output and return encoded fragments. We also use Merkle tree to bind the coded fragments such that the retrieving party can use a Merkle tree route to detect f+1 consistent fragments to successfully decode the broadcast output. After applying the provable broadcast, the message complexity is reduced by a big ON factor, and the concrete communication bits may be reduced to only 33% of the honest of that in HoneyBadger and Dumbo in the best case. Nevertheless, MVBA is still dominatingly slow component and needs dozens of rounds to terminate. So we need to push this critical module more compact if we aim at a much faster asynchronous consensus. Unfortunately, existing MVBA protocols have similar TET structure. Take Abraham et al.'s design as an example. First, I use 4 probable broadcasts to generate and deliver a key proof, a log proof, and a commit proof. Then 3 rounds are used to terminate all these broadcasts and use 1 round of coin flip to randomly elect a party. After all of this, a view change round is also needed. The above complicated structure is fairly tight. Say if we remove any probable broadcast, we may immediately have a termination or agreement issues. Thus, it's rather challenging to push it more compact. We develop a new MVB protocol to significantly compress the protocol structure and overcome the pre-mentioned issue. First, we use coin flip in a clear box manner instead of a black box way, so we can save 2 rounds after the probable broadcast. Second, we also remove the 2 probable broadcasts, and in order to restore the termination and the agreement lost due to the removed broadcast, we replace the previous view change phase by 2 binary voting phase. And more importantly, we carefully embed the threshold signature in the pre-vote phase, and also we do similar thing in the vote phase, such that we can ensure if any node output a value, we can have a threshold signature generated to fix this value as the only possible protocol outputs in all following protocol iterations. We also add an optimistic shortcut for quick termination after random leader election. For example, if a node realizes it receives the leader's second probable broadcast finished proof, it can just direct output because the finished proof also uniquely fixes MVB's output, so it can just transfer the finished proof to all other parties and then simply output. As such, a more compact MVB protocol called speeding MVB is designed. In comparison to existing MVB protocols, speeding MVB saves about expected 12 rounds in the worst case and reduce 6 rounds in the best case. So put everything together, we can use speeding MVB and the cheaper probable broadcast to instantiate faster asynchronous common subset, and we call it speeding Dumbo. We evaluate the performance of speeding Dumbo and its components in up to 150 nodes across 5 continents. First, we evaluate the effect of the cheaper broadcast alone. When the scale is larger than 100 nodes, the reduce of basic latency becomes significant. This reflects the asymptotically improvement in the message complexity. And for all scales, the peak throughput is nearly double. This is because we save up to 2/3 concrete bit by the cheaper broadcast. Then we compare speeding MVB to other existing MVB protocols. Speeding MVB is always the fastest implementation for all system scales. That is very clear to see. Finally, we evaluate the improvement of speeding Dumbo over Dumbo. When scales lie between 4 and 82 nodes, latency is almost half. For all tested scales, the peak throughput actually is doubled. To sum up, we present a more efficient construction of asynchronous common subset with optimal message complexity. It also reduced the concrete bit communication complexity in realistic one setting. Our core contribution is a new speeding MVB protocol that only spans expected 12 rounds or less, and is 2 times faster than existing such protocols in the one setting. The above technique gave us much more efficient asynchronous BFT consensus that realized the doubled peak throughput and half the basic latency in comparison to Dumbo. Thank you so much for your attention. Any questions?